Hi, my name is Satvik Bhaskar Pandit, and today I'll be presenting an overview of the ICML 2020 paper BLIP, Bootstrapping Language Image Pre-training for Unified Vision Language Understanding and Generation. I will be going through the key ideas, methodology, insights, and overall strengths and weaknesses of the paper. First, on to the introduction and motivation. Why BLIP and what are its benefits? Well, the main motivation of vision language models in general is to build intelligent agents that can understand the world through vision and language inputs and communicate with humans through natural language. In this regard, vision language pre-training has emerged as an effective approach where deep neural network models are pre-trained on large-scale image text datasets to improve performance on downstream vision language tasks such as image text retrieval, image captioning, and visual question answering. Without pre-training, the model needs to be trained from scratch on each downstream task, which leads to overfitting and degraded performance. In comparison to other models, which cannot adapt to several VL tasks, BLIP shows state-of-the-art performance on 7 VL tasks. Second, while other models may not model multimodal interaction well, BLIP can handle both single and multimodal input while simultaneously modeling multimodal interactions quite well. And third, other models have no notion of data quality, while BLIP prioritizes data quality along with data quantity, which is a key factor to its success. Now we go through the pre-training architecture, which uses a multimodal mixture of encoder-decoder, or MED for short. The three key modules of the MED are 1. The unimodal encoders, which get the encodings of the image and text independently. 2. The image-grounded text encoder, which uses cross-attention to model image-text interactions and obtain representations of the image-text pairs. And 3. The image-grounded text decoder, which uses cross-attention and causal self-attention and is trained with language modeling laws to generate captions. Coming to the unimodal encoders, the images are first divided into patches encoded as a sequence of embeddings, then fed into a vision transformer. For text, the CLS token is prepended to each text, then fed into a BERT model. As for the pre-training objective, the image text contrastive loss, or ITC loss, is used, which brings the representations of positive image text pairs closer in the embedding space, and those of negative pairs further apart. The ITC loss incorporates momentum encoders inspired by the MoCo model, which maintains two queues to store the M most recent image and text representations. The entire details and mathematics of the ITC loss are given below. Note that VCLS and WCLS are the embeddings of the CLS token for images and text respectively. But in short, the image to text and text to image similarities are calculated, softmax normalized, and the ITC loss is subsequently calculated, which is a form of categorical cross-entropy loss. The image-grounded text encoder aims to obtain the multimodal representation of image-text pairs by injecting visual information into text. This is done via cross-attention between the self-attention layer and feed-forward network for each transformer block. Except for the inputs, cross-attention is similar to self-attention. It asymmetrically combines two separate embedding sequences. For BLIP, the image serves as the query input, while the text serves as the key and value inputs. Here, the encode token is prepended to the text. The output embedding of the encode token is used as the multimodal representation of the image-text pair. The pre-training objective for the encoder is the image-text matching loss, or ITM loss. ITM aims to learn image-text multimodal representations that capture the fine-grained alignment between vision and language. Given the two-class probability P and two-dimensional one-hot vector representing the ground truth label Y, 1 if the pair is matched and 0 if the pair is unmatched, ITM is formulated as a binary classification task with a cross-entropy H between Y and P as the loss. Finally, the image-grounded text decoder. The image-grounded text decoder aims to generate textual descriptions conditioned on the images. The normal bidirectional self-attention layers, which are present in other modules, is replaced by causal self-attention, which only looks at the context to the left to predict the next token in the sequence. Note that here we are not training a discriminative model or learning embedding of words, but training a generative model to generate text, so masked language modeling isn't used. Instead, causal language modeling loss, or simple LM loss, is used as the pre-training objective, which can only see words generated to the left, which makes sense for generating captions. Mathematically, LM loss is the cross-entropy loss over the entire text vocabulary. it trains the model to maximize the likelihood of the text in an autoregressive manner as words for the caption are generated. Regarding the overall pre-training workflow, the three pre-training objectives mentioned in the three previous slides are jointly optimized with two understanding-based objectives and one generation-based objective. Each image-text pair requires only one forward pass through the more computationally expensive visual transformer and 3 forward passes through the text transformer. Additionally, the text encoders and text decoder share all parameters except for the self-attention layers. This improves training efficiency and decreases computation time while benefiting from multitask learning. It is interesting to note here that the multimodal interaction is modeled in 3 ways. 1. The image-text contrastive loss, as the error in aligning the representations is backpropagated to both the vision encoder and text encoder. 2. The cross-attention between the encoder and decoders. And 3. The image-text matching loss, which is explicitly trained to have a higher similarity score for positive image-text pairs. Now we come to the focal point and difference maker of BLIP, capfilt. Owing to the time and money constraints, there exists a limited number of high-quality human annotated image-text pairs. An alternative to manual labeling is to utilize a larger number of image and alt text pairs that are automatically collected from the web. However, these alt texts often may not accurately describe the visual content of the images, making them a noisy signal that is suboptimal for learning visual language alignment. Here's where capfilt comes into play. Capfilt comprises two modules, a captioner and a filter. The captioner is an image-grounded text decoder fine-tuned with the LM objective to generate synthetic captions for web images. The filter is an image-grounded text encoder fine-tuned with the ITC and ITM objectives to learn whether a text matches an image. The overall process goes like this. The original human annotated images and unfiltered web images are first pre-trained with the MED. After the captioner and filter are fine-tuned, both the original web text and the synthetic text from the captioner are fed into the filter to remove noisy text. A text is considered to be noisy if the ITM head predicts it has unmatched the image. The filtered image text pairs with the human annotated pairs are then recombined to form a new bootstrap dataset which is used to pre-train a new model. This process can be repeated several times. Note that the captioner and filter are fine-tuned using a high-quality human annotated dataset such as the COCO dataset. The two are fine-tuned individually to prevent bias that would occur otherwise by noisy captions being produced that are less likely to be filtered out by the filter. The structure and training objectives of capfilt make it easy to integrate with the MED. Having mentioned the details behind pre-training, we now move on to fine-tuning. To perform different visual language downstream tasks, different paths of the pre-trained model are fine-tuned to achieve different objectives. Here, for example, for visual question answering or VQA, the image question is first encoded into multimodal embeddings and then fed into the answer decoder. The VQA model is fine-tuned with the language modeling loss using ground truth answers as targets. For image captioning, the model is fine-tuned on the COCO dataset with language modeling loss. The text decoder produces a caption with the help of the image encoding. To perform image text retrieval, given an image, the feature similarity scores for all the image text pairs are calculated. The top K candidates are chosen and their ITM scores are used for ranking. The value of K can be set to a small value for faster inference speed, which is much more effective than computing ITM scores for all the pairs. The same approach can be used for text image retrieval. Similarly, using different combinations of the modules, BLIP can be adapted to other visual language tasks such as natural language and visual reasoning, visual dialogues, and even zero-shot transfer to text-to-video retrieval and video question answering. Finally, to conclude, here are some strengths and weaknesses of BLIP. Coming to the strengths, 1. It can be used for several visual language tasks via a simple combination of different modules. 2. It captures intermodal interactions quite well, as previously mentioned. 3. It uses generative modeling and all text pairs from the web to increase the size of the dataset. And 4. Prioritizes data quality by making use of a filter. Coming to the weaknesses, primarily it contains bias towards COCO data as the captioner and filter are fine-tuned on a single dataset. Additionally, the downstream tasks may be similar to the COCA dataset, so results may or may not represent the model's true generalization capability. 2. Since different modules share parameters and tasks could be drastically different, catastrophic forgetting could occur. That is, the model would abruptly forget previously learned tasks upon learning new tasks. 3. Training can take lots of time, and to pre-train a new model after every bootstrapping round would be computationally expensive. Furthermore, each bootstrapping round may lead to quickly diminishing returns in performance. And finally, although it can be incorporated, a module to generate images given some text could have been included. I hope the presentation was an insightful one. Here are the references used in the various slides. Thank you for watching.